Hi everyone, welcome to the seminar. Today we're very happy to have David Inouye speak for us. David is currently an assistant professor in the Electrical and Computer Engineering Department at Purdue University. His research interests are broadly in trustworthy machine learning, which aims to make ML systems more fair, robust, causal, and explainable. And currently, he is interested in advancing distribution matching fundamentals, algorithms, and applications such as causality, domain generalization, and distribution shift explanations. And before Purdue, David was a postdoc at Carnegie Mellon University working with Pradeep Ravikumar. And before then, he got his PhD in computer science at the University of Texas at Austin. And today he's going to tell us about trustworthy machine learning via distribution matching. It's all yours, David.
Thanks so much, Lee. Thanks for having me. It's a privilege to be here, virtually, I guess. I'm happy to hear any feedback you have on the talk or any questions or confusions, or if I've added some fairness stuff, and you're probably more of an expert on fairness than I am. So if there's something wrong, please let me know if I didn't get it correct. So I'm happy to hear any feedback. So yeah, let me just go ahead and jump in here. So while ML has made great strides in recent years, ML still has many issues. For example, large language models could compound historical bias against minorities. You have autonomous driving systems that, if they see unexpected conditions, that could cause loss of life. Medical ML systems, right? If they make false kind of counterfactual predictions, they're predicting something will happen when in fact that's false. That could recommend some sort of fatal treatments to people, or scientists may make some incorrect scientific conclusions based on some black box models that they've trained to kind of do some sort of prediction. So these could all be issues that haven't yet been solved, I think, and there's still a lot of work on these. So the next generation of trustworthy machine learning will need to exhibit some properties beyond accuracy. It's probably familiar to many people here. This includes things like fairness, robustness, causality, which we're getting more into and excited about, and explainability. For example, how can you explain a distribution shift when there's lots of distribution shifts are now kind of ubiquitous, but how could you explain the shift itself? So these are just some aspects of trustworthy ML. Now, for the purposes of this seminar, I'm going to focus on the fair classification or fairness examples, but I'm kind of going to briefly touch on a couple others. But let's start with the fair classification example. So usually the basic idea is optimize performance, given some sort of fairness constraint. So the notation I'll use, F will be a classification model. X, Y, and D and Y hat will be the inputs, the label, the sensitive attribute I'll denote by D here. The model's prediction will be Y hat. So you can assume there's some sort of joint distribution over these X, Y, D, and Y hat. I put a little subscript F here to denote that, right, Y hat depends on F. So this distribution does depend on the F you have, whereas the X, Y, and D are kind of, the population level distribution, but Y hat does depend on F. So one fairness definition, demographic parity. This measures the difference between the predicted probabilities between groups, right? So you say you want to, in the binary classification, binary case where you have only 0, 1, right? The probability that Y hat equals 1, so you predict positive, between group 1 and group 2 should be close to 0, right? So this is measuring the difference between these, and you want to ideally push this to 0. So you can frame the fair classification problem as basically a task objective plus some fairness constraint, right? And our task objective here is, probably some sort of standard classification loss or just accuracy 0, 1 loss. So that's your task objective. And then you have this constraint that you want your demographic parity gap to be less than some delta here, where delta could be 0, in which you have like 0 unfairness in that sense with respect to this demographic parity. So this template here, I think is how actually a lot of trustworthy ML applications fit, is basically this task objective and then some sort of constraint. Now, there we go. So this fairness constraint can actually be satisfied via distribution matching. And so I'm kind of going to slowly build up my argument for distribution matching. So first, you can note that this demographic parity gap is actually total variation distance between these two distributions, right? The distribution of y hat given d. So you're really saying that this total variation is less than some delta. This is actually a distribution matching constraint on p y hat given d. You want the distributions p y hat given d equals 1 is equal to all other p y hat given d anything else, right? In this case, there's just two d's. Okay, so this is actually one matching constraint. Now, just to kind of generalize a little bit in practice, the model is often decomposed into two parts. One is some sort of feature extractor or representation learning G here that takes in both the input and possibly the sensitive attribute D. And we get this Z, latent representation. If you kind of decompose it in this way, you can also write kind of the task loss with respect to G, this representation you're learning. So we have a task loss with respect to G is actually a minimization problem over kind of the classifier head that you would put on top of things, and then your normal classification loss, right? So now if you kind of take this representation learning view to ensure demographic parity fairness, a sufficient condition is actually to ensure that the latent TV distance is small. So this Z, the distribution here, these distributions here, right, which is some intermediate distribution. If that is less than delta, then we also have that the demographic parity gap is less than delta. And this is by the data processing inequality for F divergences. Okay, so you can kind of create a sufficient condition. If I match it up in some latent space, any pre-processing I do after it will also be matched, right? So this is actually a distribution matching constraint on this distribution, some intermediate distribution before the final y hat prediction. Does this seem? Any questions here? I'll pause for a second, but.
Makes sense.
Sorry, I had a question. So how come in the last line the left-hand side depends on the classifier F, but the middle expression only depends on the distribution of XYD? So I'm trying to see.
Yeah.
Why is that?
It's a little bit of an overloading of notation, but I use F here to denote the combination of F and G. So you could replace this with F classifier, compose, and G together.
Oh, I see.
And then this one is just G. So this part actually doesn't depend on F class. It only just depends on G.
Oh, okay. So you actually learn G as well. Okay, thank you.
Yes. So you'll end up minimizing over G this loss under this constraint. But then it's a min
Right.
G, min F. So you could combine them, of course, and just make a min over F and G together.
Right. Thanks.
Yeah, great. Thanks for the question. So this is just one example. I'm going to try now to immediately go to what I think of as a good definition following this basic template, right? So I think that distribution matching for trustworthy ML takes the form of task constraints. So what's important is you're always going to have some sort of task objective. I think some of the confusion with distribution matching is by itself, it's actually not that useful. You also need some sort of task objective for it to kind of be a useful thing, because there's a trivial solution usually, right? So you can satisfy this constraint trivially often. And so there's always going to be a need for some sort of other task objective that's kind of useful. But then you want some sort of matching constraint. And this, in the most general form, I'm going to let the latent distribution be a function of x, d, and epsilon, where epsilon could be some noise. So this could be a stochastic mapping. And it could depend on d, but may not. So it's, in this general form, it could depend on both, but in practice or in certain contexts, you might not depend on d or might not depend on epsilon. It's just a direct mapping to x. We'll talk a little bit more about that in the next couple slides, but you also need to define some set of functions. Sometimes that set of function is just from practicality. Sometimes it's from constraint. Suppose you want it to be invertible, things like that. I'll talk a little bit more about that later as well. So we're going to denote this G to be a matcher. I'm just going to call it a matcher. And you have some divergence, KL divergence, Chance-Shannon, tonal variation, anything. I guess, this is the kind of theoretic setup if, we're not looking at algorithms yet. So some sort of distribution divergence. And then you can see either the hard constrained version, you're minimizing over some G of some task objective subject to this kind of matching constraint on the latent representation. And here we have kind of the regularization version of this, which of course is often what's done in practice, is some sort of regularized version as well. So now to give a little intuition behind this, let's look at, I'm just looking at this example. Suppose you need to take this two-dimensional distribution here, and you need to rotate it. And then, we're going to assume that we have a simple class, which is a rotation and then a 1D projection onto Z1, right? So I can rotate it and then I project it, just along the x-axis. As you can see, this is going to be partially matched. This is the kind of pretty far away. The divergence would be high. This would be a little bit closer, this middle one. And then if you rotate it enough, you can get kind of this distribution to match exactly, right? So this will be delta equals 0. This would be a solution to that, right? So you're learning, the idea is you're learning this rotation in the projection map such that this latent Z, the distributions between, in this case, blue and red, match up. You can think about this in the two-dimensional case. Here's another example. Here we have two distributions in the observed space, x1 and x2. I'm learning a mapping. In this case, I'm going to assume that the red points stay where they are. So g of x2 just equals x itself. It's just the identity map. And now I'm really learning g of x1, which is how do I map the blue, the blue points to match the red point distribution. This is what we'll call a translation map. So this is a two-dimensional map in which you shift, you move the points, you learn some map that moves all those blue points to overlap with the red points. So as I was saying, there's you can have different structures, and I think this sometimes is one of the confusions, is that there's actually different structures depending on context. So one simple case is this translation matcher. Again, you have the identity for one of the distributions, and then you have some sort of map for the other, right? And this, this actually is pretty close to what a lot of generative models are, right? So a GAN would be, you have your samples and you have your normal distribution, which you can generate infinite number of samples. And you're just trying to learn a map from a Gaussian to the original distribution, right? You keep the original distribution in some sense as fixed, and you're taking Gaussian samples and trying to map them so that they are aligned with the observed distribution. You could also have this shared matcher. So in this case, we don't depend on the attribute, the domain label here. So it's shared, this could be like when you're doing fairness, it's like whatever representation function you have, you'll just ignore the domain, like the sensitive attribute, at least in the representation. So you apply the same representation function to both males and females or something like that. So that's something even like in this example, right? It is a shared matcher in the sense that you're rotating this joint distribution and then you're projecting. Now, the only reason in this case, right, the original joint distribution is obviously not matched. So in order to do matching plus shared, you have to lose some information, right? Which happens when we do this one-dimensional projection. So take the two-dimensional data, project it. So in some subspace, it's matched. Makes sense. So that's another common version, is some sort of shared matcher. Invertible matcher is another one which G has an inverse. You can enforce this approximately, of course, using something like cycle consistency, which is what CycleGAN and others have done very similarly. So that's another possibly an inductive bias, depending on the case, or it's useful if you are working with something like normalizing flows. And then also I like to just talk about a stochastic matcher where, this epsilon is some exogenous noise, and that allows us to cover things like a variational autoencoder type methods, which I'll hopefully get to later. Okay, so this G is fairly flexible, could depend on the context, which ones you're going to use, and what those things mean. As a brief aside, I also want to say that distribution matching has been known by other names in different contexts. And so I think there's actually a lot of hidden distribution matching that you might have already come across. So in the generative models community, it might be called distribution alignment. In the robustness community, it might be something about domain and variant representation learning. If you're in the GAN-based community, there's just adversarial representation learning almost always has a matching constraint, because that GAN objective is essentially an attempt to do distribution matching. You also might think of mutual information minimization. You're trying to, make two things independent. So those are basically, it has been known by other things and sometimes a little bit hidden in terms of what it does mean. Okay, pause there for a second. Is there any questions? All right. So hopefully that gives the real core basics. And now I'm going to switch to a little bit of a generalization that I think is underappreciated currently, which is doing this for conditional distributions. So can we actually generalize this concept to conditionals? Yes, I think we can, but we do need a notion of conditional divergence. And so that's what I'm going to provide here. So you have some sort of two index sets, some splitting of the variable, the latent variables. I'm gonna, I don't know of a definition like this, but I think people kind of define it when they need it. But if you happen to know of like a reference for this, let me know. But so I had to kind of come up with what I think of as a reasonable definition of a conditional divergence. It has two properties. One, it is non-negative, like a normal divergence, right? So no matter which P and Q you put in here, it is non-negative. I'm also going to assume this conditional distribution equality. So when this is equal to 0, if and only if these conditional distributions are equal for all possible conditionals ZB. So all possible, values in the support of ZB. Right. So you're actually kind of matching all the conditionals. These are the two basic properties I would have on this. One of the most common, and I think as far as when I've seen it used, is essentially this. So you take an expectation over all possible distribution over ZB, assuming that it supports kind of match the normal the support of the joint distributions, and then you use a normal divergence here, kind of by comparing these conditional distributions. So given any ZB, right, any particular ZB, you're going to match that conditional distributions.
How do you define Z sub A and Z sub B again? Like, those are index sets.
Right. As in, like, the context will usually depend on what A and B are, but I think you were asking maybe something different.
Yeah, like what is Z sub A and Z sub B?
Oh, okay. This is supposed to be like the subvector, right? So like if you have Z1, Z2, Z3, Z4, let's say, right, in a vector, then I might say that this, for example, is this subvector is Z sub A, and this subvector is Z sub B.
I see.
Right, so
You're assuming that you're
Is there something else I can help with?
I activated my theory by accident. Yeah, sorry for that. You're assuming that you are in an n-dimensional space, maybe vector space.
Correct. Sorry, yeah, that should have, this is the dimension of the latent space.
Okay, thank you.
Great question. Yeah, that was good clarification. So what importantly, we're allowing both the conditional part and this part, both of them to be learned, as in they're not observed or fixed necessarily. They could be both learned. Now, maybe some of them are fixed. For example, you could say, as we'll see, ZA equals X1, let's say, and you fix X1, or something like that. But in its most general form, both the conditioning and the distribution you're looking at could both be learnable. And this distribution, the one you're taking the expectation over, could also be learnable, at least in the most general form, right? Because the Z here, I guess this will usually be dependent on G. You could, of course, do something like a max over ZB in the support would also satisfy this, for example. But expectation is the most common. Okay, so now you can see once you get that, it's pretty straightforward, right? About how you do conditional divergence. Oh yeah, this is right. So, you're in some senses, the input, as I'm defining it, the input to the conditional divergence is over all of the Z's, right? Like the joint distribution over Z, or the marginal of Z. But obviously, as you split it up, it'll be comparing each of the conditional distributions with respect to those sets A and B, right? So it's kind of like the input is still just the whole distribution of Z given D, but then, it is 0 if and only if this thing. Now, it's trivially true that if the joint distributions are matched, right, then any conditional distributions are also matched, right? But the opposite doesn't necessarily hold, right? So this is an example, right, where again, you're learning a rotation from this is the joint distribution here. In the case, the red is one distribution and blue is another distribution. And you're learning a rotation in this case. So you learn, say, this rotation. Now the conditional of Z2 given Z1. So you kind of look at each of these conditional slices. They actually line up. So that's why it looks like this purple color, because they Any slice lines up, even though the marginal distribution, right, will be different here. So if you take the marginal across this, right, the red is shifted from the blue in terms of the marginal of Z1, but Z2 given Z1 is aligned here. So you can get conditional alignment without getting joint alignment, just as you could get marginal alignment without joint alignment. Here's another 2D example. Here, I again assume that this the blue points stay fixed. That distribution is the identity. And I'm learning a representation of red, a new representation of red, right? Where the conditional distribution aligns. So now, you know, they're all kind of along this with some noise, right? So the conditional distributions will align, even though the marginal distributions of Z1, in this case, right, there's more red on the outside, for example, the marginal distribution doesn't align. So it's kind of a weaker constraint than a joint distribution matching. I'm going to do one more example of this conditional matching here. So suppose you want a binary, you want to kind of match this probability of y given some z. So in this case, we're going to assume that the z that we're talking about up here is actually two things. One is y, the original label, and one is z tilde, some learned feature, right? Okay. And our script A set will be 1, and our script B set will be 2. So it's going to extract, you know, script A is Y, and script B refers to Z tilde. So for every value, so if we're kind of taking for any particular value, let's say this is Z12 equals -5, let's say, we want that the probability of Y equals 1 is equal to this probability down here. We want the blue and red to match, but we want it to be matched for every Z tilde. Right. Actually, yeah, this should be Z tilde here, sorry. So given Z tilde, you want to match between the red and the blue line, which is the different domains. So it's saying that I want every single point between these, right? I want each of those to match. So here, of course, on the left, you have mismatch. In the middle, you have kind of some partial matching, right? And then on the right, you have this matching where across the distribution, this y, the distribution of y given Z tilde is matched across D. So this is actually related to invariant risk minimization. Invariant risk minimization could be seen as kind of approximating this, where they're trying to learn some Z tilde, where the distribution of y is matched across the domains, is invariant across the domains. And they do this by doing this bi-level optimization, right, where you try to essentially approximate this actual, kind of true distribution of y given the Z tilde, the features that you've learned. Okay, any questions on conditional distribution match? Great. So now let's go back to fairness a little bit. So I've tried to think about how do I taxonomize some group fairness measures. Most of these are group fairness. So of course we have here demographic parity on the left. that can be thought of as marginal matching. Y hat in some senses is the Z that you're learning. And in this case, the matcher that we're learning is actually just the classifier itself. Okay, so you're matching that, and demographic parity tries to match those distributions. Then from there, you can split off into conditional matching here. So now we condition on, say, the true target label, Y. And this is where you get something like equalized odds. Right? So Y hat given Y. So within the group, qualified, unqualified group, within that group, how well do your predictions is fair across your sensitive attribute. You could also think of, I don't know how many people have done this, but conditional equalized odds, where you kind of condition on some set of features. Now you could choose, these might be chosen, say, based on causality or some prior knowledge that it's okay to condition on those. Say it's a job requirement, then, there are some features people think of, at least, that could be reasonable to use for particular jobs, even if they may be correlated with, say, gender or something. Okay, so those, of course, you'd have to decide very carefully. But similarly, if you go down here, you can get conditional demographic parity, right? It's still conditional. You're conditioning now on X1 or some set of the X's. So those are the possible, you can have a whole slew of possibilities there. And then if you look at the end here, so let's suppose the original dimension, so M here, I'm also using to denote the dimension of the observed space. So if you condition on all of the dimensions, that's actually going to be individually fair, because every single point, right, you can kind of do whatever you want for every single point, and it's still going to match up. So I think this is actually kind of a continuum between group fairness and individual fairness, is actually this conditional stuff in between. I mean, there's obviously other views of individual fairness, but just wanted to point out that those themselves are individually fair. And there's other ones like sufficiency, where you have Y given Y hat. I don't know as much about that one, but that one is also like could be considered another type of fairness. So you could also, just like we did before, we kind of using that data processing inequality, you could also take this as, in practice, we could maybe learn some Z class here and condition on any number of other latent variables. So we just replace Y hat with Z class, then you do some classifier on top of Z class to get your Y hat. That will, in the end, be kind of equivalent. So this kind of generalizes the notion if you have some latent representations. Again, if the matcher is shared, right? So if we ignore D here, then this can be seen as achieving fairness via feature suppression. So we're kind of trying to remove any features or any kind of combination of features that has any information about the sensitive attribute, right? So you can think of it as like dropping some of the features, like dropping all features that have that. Of course, we're learning a latent representation, so it's a little more complicated, but you learn some transformation such that you've kind of removed all of that information, but you're applying the same function to both groups, right? So you're learning some kind of viewpoint or perspective on those groups in which they look the same. This would also satisfy individual fairness, because once you put a classifier on top of this, this is just a function of X. So you're giving the same prediction for every X, whether they come from one group or the other group. If the match is not shared, so G does depend on D, then you might violate individual fairness. And this has been one of the big things, right? You apply a different prediction function based on race, for example. because you're kind of, even though you're learning a match distribution, that G function will be dependent on D. And so it would give different predictions depending on D.
If the matcher is shared, like still different X's will get different outcomes towards the end. So I don't see how that satisfies individual fairness. All we know is that it doesn't depend on D, but different X's are assigned different G to, like, yeah, representation, and after when they're applied the F function, they're gonna get different outcomes.
So I think it means maybe there's different notions of individual fairness, but I think at least what I'm trying. So maybe I should talk offline if I'm doing this wrong. But my sense was if like a male has the same features as a female, they should have the same prediction probability. Is that right?
Yeah,
so this will be that's one.
Yeah, I mean that's a valid notion of fairness, but I think that's more on the like group notions of fairness. Like it's you're equalizing males versus females. Yeah. So you're giving guarantees such that males have the same, or at least according to the notion of fairness that says representation doesn't depend on the feature, I guess, according to that notion of.
Right. According to that kind of
possibly
problematic definition.
It's individual fairness if you adopt this metric that just equate people where you flip this gender attribute, but that's not necessarily the right metric to look at. Because some features should potentially be interpreted differently for different genders.
Right. So yeah, this is individually fair in the sense of blindness to the feature. Of course, is it truly blind? It depends more semantically. Is there correlations that matter and so forth? But yeah, so definitely. Thanks. Okay, so this is fair classification. Oops. Fair classification is one of the trustworthy ML applications. Distribution matching. Obviously, there could even be other distributions that you match here that we talked about, but just kind of there actually are different algorithms and different matcher structures that people have considered. Just to go over a few other applications. Domain generalization. This is where you have a different test distribution than you had at training time. So when there's a train test distribution shift, and you want to generalize under that shift. There's actually a lot of different things people have proposed, very different kind of distributions to match. IRM here, that was the one I kind of showed, like you're trying to match the true distribution of Y given some features that you're learning Z. And so that's like trying to match up the kind of the optimal predictor given Z. So that's a very different, obviously the other standard one is like a domain adversarial neural networks that just tries to match the features in some latent space. And then even some other methods try to match the gradients with respect to the loss. So you can think of that as another kind of learned representation based on gradients. So I think these are, in all of these cases, you're generally going to assume a shared feature extractor, because if there's a new domain, you don't usually know what the domain label is. It's not going to be a previous domain. It's going to be a new domain. So you need a feature extractor that doesn't depend on the domain label. So it's going to be some sort of shared feature extractor. And I do these little stars to show some of the work that my group has done on some of these areas. There's also causality. So I'm estimating causal average treatment effects. as well as determining kind of causal order can be seen as this. And we've looked into domain counterfactuals, more complicated constraint, but this can be applied in those. And then there's also distribution shift explanations. We have a paper on this. There's sparse or interpretable transport. So where this is really pulling from the optimal transport literature and saying, oh, can we do optimal transport, but do it in such a way that it's interpretable? So that's kind of the basics of that. All of these can be thought of as applications of distribution matching. Now, in this case, for example, the task loss is more transport cost or some sort of regularized transport cost. So you can see that there are different possible task losses along with different possible distributions to match, along with different structures that you might impose on your matcher that give you different properties that you might want. Okay, so some analogies to summarize. I like to think of, classification is to current ML, right? So this is this very common, this kind of core concept and algorithms and such that is common to current ML. And then what, in some sense, is analogous to that is to trustworthy ML. So some people might scaling data or models. I think that could have some real impact for robustness if you just kind of assume that you've seen everything that you need to see, then maybe that would work. But I still don't think it, it doesn't make things fair, right? Like you scale up, you're still going to have bias in the data. So for example, fairness, I don't think it's just scaling the data or models isn't immediately going to solve that issue. You might also think application-specific design. So some very carefully constructed either architecture or constraint, mathematical constraint. I don't think it's as broadly applicable as classification, right? Classification is used in all sorts of application domains, right, as a core problem, and they use generic algorithms. They don't have to kind of redesign the algorithm every time. So as you might have guessed, what I think of might be this. Of course, you're welcome to disagree. Is distribution matching might be this kind of more general. So it's fundamentally different than classification. It's not just a different supervised learning objective. It actually, the overall goal is quite different than classification itself. And in contrast to application-specific design, I think it's going to be broadly applicable to different tasks, as we've seen in the past. Now, why do I think it can be an enabling tool, even longer term? So one fun analogy, so classification I think of as Tigger, whereas distribution matching is like Eeyore. So a bit of optimism versus pessimism, maybe a little bit more technical. I think classification kind of as an example of this task objective, whereas distribution matching is like task constraints. So it's kind of a positive goal and some sort of negative constraint, something like performance safety trade-off, that kind of thing. So I think distribution matching has the potential of really being this very general way of specifying task constraints if you define it right. And then why do I think this could be more broadly applicable? Like why is this kind of generally useful, like classification has been really broadly applicable? So class labels are to classification, a little analogy here, as I think domain labels are to distribution matching. And why do I think domain labels are interesting? So they're really data driven in the sense that, how you specify the domain labels specifies your constraints implicitly. I think it's really easier to elicit from experts than some sort of formal definition of their constraints. And in some cases, the domain labels are just metadata that you might already have. But it's also potentially easier to elicit these constraints rather than going to a domain expert and saying, hey, can you mathematically write down the partial differential equation that satisfies the constraints you care about? That's, again, going to be hard, just like formally defining what makes a cat is hard. Similarly, I think formalizing constraints is hard. But maybe if we can kind of start thinking in a different way about domain labels and eliciting those from experts, we might be able to add constraints that are easier and could use some generic algorithms, just like classification. You give me class label and input, I can use a relatively generic algorithm to do that for you. So if we can come up with some good generic algorithms, I think that would be really cool. And then what is distribution matching? One last analogy here. I think you have divergence maximization is to classification, as divergence minimization is to distribution matching. This is where I really see the opposites here. If you see that you can view classification as trying to find a latent space that separates the classes, right? You want to be able to separate this distribution from this distribution. Distribution matching is just minimizing where you can't separate between these two distributions, right? So you align these and you match them. So you're still doing something with some sort of distribution divergence, but you're minimizing it instead of maximizing that divergence. Okay, so I think prior work has not really focused on this, partly because distribution matching by itself is really useful. I mean, just think about a linear constraint without an objective. It's just kind of not usually that interesting. You usually need an objective as well as the constraint, where the constraint can make it really interesting, but usually you also need an objective. So I think that's one reason people haven't focused on it. Also, other people only think of it in terms of one algorithm. You're probably most familiar with, say, the adversarial algorithm to do this, but there are other approaches, and I think we should, as a community, think more broadly about it. And distribution matching has really been investigated kind of in its own right. So I'm hoping to kind of, as you've seen, propose a bit of a unified framework here to kind of we've already covered some fundamentals and applications. I'm hoping to kind of unify some of this more into algorithms and evaluation as well. So now, hopefully, a few more minutes, I'll cover a few algorithms. So how do we actually do this in practice, right? So we've kind of formalized what the problem is. How do you actually do it? Roughly, I categorize these into three main ways of doing it. One is adversarial matching. Again, this is probably the most common. Easy to implement. You add a discriminator. You form a min-max problem, but it's challenging to optimize in practice. Likelihood-based algorithms, so based on normalizing flows or variational algorithm coders, these are things that we've worked on, less well known. I do think they're more stable, but they also have some of their own issues, and I'm wondering if we can scale them up is one of our current big questions. There are some other algorithms as well. So optimal transport-based algorithms are very common as well, using kind of sinkhorn algorithm. We've also considered this iterative matching, which is like a projection pursuit type of algorithm. So let's look just briefly at what these, I want to focus a little bit on these variational algorithms. They form, what you're going to have in this case is you're going to have some lower bound on a divergence. So for any h in the adversarial case, so for any h you have here, this part here will be a lower bound. And obviously you want to get the best, tightest bound possible. So you can maximize over h to get the tightest lower bound you can get. And then prove that, if h is kind of arbitrarily complex and, you allow it to be any function, then this whole thing together can actually be tight. And for example, in standard GAN, this would be the Jensen-Shannon divergence. So if you make this perfectly tight, this is equal to the Jensen-Shannon. If it's not tight, it's going to be a lower bound. You could do this for other divergences, F divergences, Wasserstein, the same basic idea of this min-max problem, this adversarial. What I've worked on is a little bit more of these likelihood upper bound based methods. So we form some sort of upper bound given some distribution Q. So again, you're forming some this upper bound and you want to make the bound tight. So you're going to do a minimization over Q, right? That's going to be the basic idea. So we generalized this to flow-based methods, and we've revisited VAE-based methods. So as you can see, I think these are kind of two sides of the same coin. They're just approaching them differently. So to give a quick sense of one of our works is on flow-based models for invertible methods. So we have this variational upper bound. It turns out it looks very much like the log likelihood of a normalizing flow. So it's essentializing the negative log likelihood, you're minimizing negative log likelihood. But in this case, we're going to assume that you minimize over that kind of prior density, Q of Z. So usually this is like some prior distribution. You're going to actually minimize over this distribution. And this is, importantly, it's that this is shared. So this distribution, it's not conditioned on D. It's just going to be just, marginal over Z, over the D, sorry. Okay, so this is just Q of Z. So it's like you're marginalizing over D. And the gap is going to be a KL term, kind of like in an elbow type of update, and some sort of constant. Again, kind of like when you're comparing KL divergence to negative log likelihood, that gap is based on these entropy terms that are constant with respect to G, the thing that you're learning. We know the bound gap is exactly this. And so any Q, this should be lowercase q, sorry, provides an upper bound. So basically for any Q here, this is an upper bound. And then of course we want to make that bound tight by minimizing. Intuitively, you have these two things going on with this double minimization now, because the outer minimization is over G, the inner minimization is over Q. Minimizing G kind of pushes the distributions to look like Q. So you can see these arrows going out. It's like pushing those distributions out. And then minimizing over Q is like trying to match the current distributions of Z, the mixture of them. So that's like these arrows going in. Q is trying to kind of push in. The blue and green are trying to push out. And if you do both of those, eventually the blue and green will match purple, kind of at least at the optimum. In our variational paper, which is on arXiv now, but hasn't yet been published, but there's a preprint, we can relax this invertibility. So it turns out I found that normalizing flows are also kind of hard to train because you have this very particular architecture that you have to follow. So instead we were saying, well, can we relax that somehow? And it turns out you can. You can actually, so you can relax this by having a stochastic encoder here, right? So this is going to be a stochastic thing. And now you're going to also optimize over this decoder function, right? So now you don't have to assume invertibility, but you need this other function to go back to the original space. And it turns out there's a nice correspondence between the Jacobian term and the ratio. So this term here and the Jacobian, there's kind of, it can be seen as a direct relaxation of a Jacobian type term. And we need this to be approximately invertible. We want to encourage approximate invertibility of G. So we kind of want to increase the reconstruction regularization, which ends up simplifying to kind of a beta VAE objective, where beta is actually less than 1 in this case. So we're kind of emphasizing the reconstruction term to kind of encourage it to be closer to invertible. All right, given the time, I'm going to skip a few more. We do some noisy things. This is the iterative algorithm. You can put all of these algorithms, you can kind of categorize which kind of algorithms they use. There's lots of different ones now. And I think there could be more that could be done. I'll skip this too. Maybe I'll skip this to get to the end too. So there's some stuff I have on evaluation, but I'm going to skip that. And I'll end with, I think there's a lot of open research, both in fundamentals, applications, algorithms, evaluation. I think we need more practical stuff in terms of algorithms and evaluation and formulating new applications correctly. For example, fair clustering, I heard some people recently talk about fair clustering, and I wonder if distribution matching can be used there, as well as causal representational learning I'm excited about. And then one last little plug for theory, maybe. So how do we assume, can we ensure a unique matcher G? There are usually many possible G's that satisfy the constraint, and even many possible G's, even given some task objective. In the case of optimal transport, we know that if you use this kind of transport cost, then there's actually a unique map G that satisfies this, and it's invertible, assuming continuous distribution. So usually there's this, many possible G's that would satisfy, minimize the objective and satisfy a constraint. So could this be generalized, right? Like if you have this classification loss instead of the transport cost. More generally, I wonder, how can we make this identifiable, this G? What kind of task losses, what kind of objectives would make this G identifiable? I think that's something that people, at least in ML, just kind of ignore, that there's so many possible G's that would satisfy this, and don't really think about, how could we make sure to find the right G? So just an open question. Happy to, if anybody has any thoughts on that. And thanks for listening. Feel free to give me any feedback over email or now. Be happy to hear any critique. I've gotten much helpful feedback from other people in the past, so be excited for anyone.
Thank you for the talk. Yeah, if you have any questions, feel free to unmute yourself and ask. One question that, like, about this last slide, why does the uniqueness of G matter? Like, if I know, maybe you explain and I missed it.
Yeah, the uniqueness of G, I've hit it a lot in causality. So often in causality, identifiability is like the key. Like, can you, under what assumptions is the causal model identifiable? So that's the time because if you can't identify the causal model, you can't actually, like, say, from some sort of observational or even interventional data, if you can't identify it, then you can't do counterfactuals or interventions correctly, or assume that you're getting close to that, right? So that's probably where I've hit it the most. But even like in domain adaptation, I've realized, right, like that domain adaptation used to just be like, match the features and then do a classifier on top, right? But the source, map the source onto the target and then do classification on the source domain, where the target domain, you don't have any class labels. Well, it turns out there's like, the target could be mapped in an arbitrarily bad way to this distribution, such that, right, the target classifier error will be really bad, right? So kind of under what kind of assumptions will this map be good versus not? This is, of course, assuming you have no labels in the target domain, right? So you have no way of orienting the target map. I think that's basically something people haven't really thought of, or like kind of missed when they were doing domain adaptation. It was just kind of seemed like a reasonably intuitive idea, but there could you could satisfy good source classification and good alignment with kind of a horrible alignment of the source and target, in a sense, like an opposite alignment of the source and target in terms of their class labels. So then you can kind of get arbitrarily bad classification on the target domain almost. So that's an example of why, like, maybe we need to think more carefully about the constraints that would actually enable us to, like, ensure domain adaptation would work well. Same with causality. How do we know it would work well?
I have a high level question, and apologies if you answered it during your talk. I went and got lunch during some portion of the talk, so apologies in advance. But okay, so like this slide is, showing us that what you've got is a big hammer that is a sufficient condition for all sorts of things, which is cool. But to the extent that what many of these are different constrained optimization problems, is there concern that by doing distribution matching rather than something more specifically tailored to the constraint in the problem, that you're sort of imposing a stronger constraint than might be needed in each of these particular tasks, and therefore, you know, by imposing a stronger constraint, you're not going to get as high quality a solution?
Yeah, that's definitely could be the case. So for example, like an example that seems to be is the difference between these two, for example, in domain generalization, like imposing that all the features are matched is a stronger constraint than imposing that the y given z are matched, right? So I think some people were like, hey, let's shift to this IRM version of matching. So I think that's definitely true. But then is it more than that? Yeah, I would think so. I'm sure for any particular application, there may be better ways or like simpler ways to do it, for sure. I think I'm just trying to think about, right? People use classification in all sorts of ways. That's probably a bad idea, but they do it anyway. Right? Like in all applications, everybody tries to make a classification problem out of whatever they're trying to do, in part because we can then easily run an algorithm for it. So I think my current viewpoint is like it'll have a broader impact if you can apply kind of a generic thing to it. But we need better algorithms. I mean, our algorithms are not very good right now, I don't think.
Yeah, I mean, I guess like if I had to invent an answer to my question off the top of my head, you can tell me if this is a good answer or not. I might sort of say, well, you know, if you're training the whole end-to-end classification technology, maybe what I said is true, but to the extent that what you're doing is releasing an embedding or some model that's going to be fine-tuned or something, and you have control over the representation, but not over layers that come above that, then, you know, distribution matching can solve these problems when it couldn't have been solved end-to-end.
Right. So it maybe one other caveat to this is that some of them I think are actually the exact constraint, like in fair classification, that is the constraint you want. In other cases, like domain generalization, it's like a means to an end. And whether that means is the right way to get to that end is unclear, right? Like domain adaptation, for example, maybe feature matching is not the right way. And just augmentation is what most people do now for like images, is like good augmentation methods can beat, you know, careful distribution matching. So I definitely think there are other ways of doing, you know, like some applications it's going to be the only way to do it, and some it's going to be one of the ways to do it.
Cool, thank you.
Thank you again for coming to the seminar, David.
Yeah, thanks so much for having me. And feel free to email me if you have any follow-up questions.